Hi, welcome if you're new and welcome back if you're not. My name is Talia. I'm a recent UCSC alum and I love making videos to teach others about chemistry. In this video, I'm going to be doing an intro on Ksp, which is the solubility equilibrium constant, and also doing a few example problems that you might see on some of your homework. So if you need help with that, feel free to keep on watching. And without further ado, let's get started. Okay, so before we get started on doing KSP problems, I'm going to go over a couple important vocab words relating to solubility. So the first two are probably the most important when it comes to solutions and solubility. They are the solute and the solvent. The solute is the substance being dissolved, and the solvent is the substance doing the dissolving. Usually this is water, in like the majority of the solutions you'll see, but sometimes it can be other things. For instance, a compound dissolved in ethanol or ethyl acetate or something along those lines. There are also two different kinds of solutions we're going to be talking about. There is a third one, but it's not as relevant to this unit. So there's an unsaturated solution and a saturated solution, and the third one is supersaturated. So an unsaturated solution is when less than the maximum amount of solute has been dissolved in the solvent. Basically, that means that you can put more solute in and it'll still dissolve. But you can't do that in a saturated solution. A saturated solution has the maximum amount of solute dissolved in it. We're also going to be talking about solubility, like I said, and this is how much of the solute dissolves in water or in the solvent. And this is going to be measured with a concentration. And specifically, if we have a higher solubility, we're going to have a higher Ksp value because that means that more of our solid is going to dissociate into ions. And we know from previous equilibrium problems that when you have a high K value, your equilibrium favors the products. And that tracks because if we have a high Ksp and a high solubility, like I said, we're going to have more dissociation. If the reverse is also true, if you have a low solubility, that means you have a low Ksp, which means the equilibrium is going to favor our reactant, which is the solid, and less of the solid is going to dissociate. So in this first problem, we're dealing with silver bromide. The solubility is 8.8 times 10 to the negative 7th molar. I have a bullet point at the top that says even insoluble compounds or precipitates have a little bit of dissociation, and that's what Ksp measures. You can also measure Ksp for a soluble salt. The Ksp will just be a lot higher. In this case, we're dealing with an insoluble salt, silver bromide. So the solubility is 8.8 times 10 to the negative 7th molar. That's how much we put in the start of our reaction, in the start of our equilibrium reaction. And we use an ice table for these problems, just like you do with regular equilibrium problems. So the idea is that this concentration of silver bromide is fully going to dissociate into silver plus and Br minus ions, which is why that's the equilibrium concentration of those ions. And in equilibrium, no more solid is going to be remaining. And the change, therefore, is 8.8 times 10 to the negative 7th. So this setup is very similar to previous ice tables, just with slight changes. So this is the amount that can completely dissociate, like I said, and that's why it turns into ions. Okay, so now we need to calculate Ksp. We know that from previous videos and the entire like basic equilibrium unit, you calculate K with the concentration of products over the concentration of reactants. The equilibrium concentration of the solid is 0 because the 8.8 times 10 to the negative 7th molar fully dissolved into ions. So instead, we just set up our Ksp expression as the concentration of Ag plus times the concentration of Cl minus. And also just a reminder, like from previous videos, if there is a coefficient in front of the ion or the reactant or any other kind of product, always when you're calculating K, you need to raise that concentration to that power. In this case, silver bromide dissociates into Ag plus and Br minus, and there's just a 1 in front of each ion, so you don't need to raise anything to any power other than 1. So now I go ahead and plug in the concentrations that we have in the equilibrium row. And I get a final solubility of 7.7 times 10 to the negative 13th. So this is small, and this makes sense because silver bromide is an insoluble salt. So it is going to be more likely to remain in the solid form than dissociate into the ions, which is why not a lot of products form. Okay, we're going to do another example, and we're basically going to be doing the reverse now. So we have a KSP of cobalt 2 sulfide is 5.0 times 10 to the negative 22nd. We need to determine the solubility. So how much of this, in this case, insoluble salt, is going to do a teeny tiny amount of dissociation into ions, and what is the concentration of each ion at equilibrium? Now, when you're dealing with a soluble salt like NaCl, you can very easily dissociate it into Na plus and Cl minus and calculate the concentrations of the ions like that. We can't do that with an insoluble salt, which is why we're using the ice table, which is what I'm going to show you in this problem. We've set up our ice table similar to how we did in the first problem. We have cobalt 2 sulfide, and then it's becoming cobalt 2 plus and S2 minus. The difference in this problem compared to other problems is that we don't know what the solubility of the cobalt 2 sulfide is, which is why we're trying to find it. So instead, we're going to say that we're putting X amount of the solid into the solution, and that's why that's the initial value. As the solution reaches equilibrium, the reactants lose X and the products add X because that concentration of ions is formed. And then the equilibrium concentration of both of the ions ends up being X. So instead of a numerical value, we're just using X. And this is the same as the equilibrium problems where you had K, but you didn't have the concentration of something in the ice table. So now we're going to go ahead and solve for the solubility. So we're going to have to do some algebra in this step because we don't have our concentrations. I'm setting it up exactly the same way as I did the first KSP expression or the first KSP equation. I have my KSP on the left, 5.0 times 10 to the negative 22nd, and that equals the concentration of cobalt 2 plus times the concentration of S2 minus. Since both of those are X, it equals X squared. And then now we algebraically solve for X, which is the solubility. And if you square root both sides, you get that X is 2.2 times 10 to the negative 11th molar. So that is the solubility. It won't always also be the concentration of each ion at equilibrium because sometimes the ions will have coefficients in front of them based on their subscripts. So if we take that solubility and form kind of like a pseudo dissociation equation, because we're dealing with an insoluble salt, we can say that because the solubility is 2.2 times 10 to the negative 11th molar, the concentration of both of the ions in solution is also that amount. If we had an insoluble salt where one of the ions had a coefficient of 2 in front, this value of X would be multiplied by 2, even though it's still the solubility. And this slide just has the same numbers written differently and in a smaller font. And I just put my final answers here and highlighted them. You always want to write concentration with brackets. So we have concentration of cobalt 2 plus and concentration of S2 minus are 2.2 times 10 to the negative 11th molar. So hopefully you see how those two examples are essentially inverses of each other. One is using solubility to find KSP, and the other one is using KSP to find solubility. So I hope you enjoyed this video on introductory KSP calculations. In the next video, I'm going to be advancing those problems a little bit and talking about what happens when you have solutions with different volumes. So I hope you'll join me back if you need help with that. And that's all for this time. Please leave me any questions or comments in the comment section below, and good luck with learning chemistry.